Here is how to make Splatoon's ink gun mechanic in Godot 4. As always, any scripts and resources used will be linked in the description below. To achieve this effect, we need to take the following steps. 1. Make a level in Blender with all faces placed in a UV map. 2. Build a system to convert world space coordinates into UV coordinates. 3. Add a sub-viewport and viewport texture with a system to paint on the viewport. 4. Set up a shader that will mix the original level texture with the viewport texture. And 5. Create a system to calculate the score from the viewport texture. To start, create your level mesh in Blender. I actually created this mesh first in Godot using the CSG nodes and then exported it into Blender and cleaned up the mesh. Once you're happy with your level model, we need to unwrap the UVs. Make sure you're in edit mode, select all your faces, hit U, and here I'm going to do a smart UV project just for simplicity. What's very important is make sure you add some island margin. Then if you go over to the UV editing tab, you can see how it's automatically unwrapped our mesh. You're going to want to spend a lot of time playing about with your UV unwrap and making sure all the positions make sense. The reason being, these two faces, here and here, aren't connected in any way. But if we position them so that they're right next to each other, when we paint on this corner here, it might bleed over into the mesh over here, and it wouldn't make sense, but it's going to happen because they're close together. Ideally, you're going to want the face here and here to be connected, and that way when you draw your texture here, it will wrap around to the other side correctly. It can be a lot of fiddling. Once you're happy with your unwrap, we're almost ready to export to Godot. First thing though, make sure that you add -col to the end of your mesh name in Blender. This will allow Godot to automatically generate the collision shape for you on import. Another thing to note in your export settings is I found it useful to export with separate textures. That way it makes it easier when we create our shader layer. Now that we have our level imported from Blender, it's time for us to figure out how to get the texture coordinates from the world position. In Unity, the raycast hit object will return the texture coordinates from the raycast collision. Unfortunately, Godot doesn't have any features like this currently implemented, so we're going to have to calculate this ourselves. Luckily, I found an excellent article by Alfred Bordish on how he managed to implement this in Godot 3. We're going to be utilising Alfred's provided UV position script, but updated to Godot 4 to do our calculation. This script works by you first passing in the mesh instance that you want to calculate the UV positions for using the setMesh method. You only have to do this once. Then whenever you want, you can call the getUV coordinates with a world position and a hit normal. It will then figure out what face was hit and where on the face the collision happened in UV coordinates. The getFace method works by first filtering out all the faces of the mesh based on the normal we provide, so only faces with a matching normal will be used for the next step of the calculation. It will then use the isPointInTriangle method to figure out if the point that we provided is within that face triangle. If it is, we'll then return the data that was calculated. The most important part of this script is the cart2Barry function. This will calculate the barycentric coordinates from the triangle and the position that we pass in. This is useful for both figuring out if the point is within the triangle and to convert into the UV coordinates. Here is the UV position script converted into GDScript2. One important change I had to make though to get this to work properly was to the getFace method. As I previously explained, the getFace method first filters out the faces of the mesh based on the hit normal and then figures out if the hit position lies within the triangle of that face. Unfortunately, if we have two perfectly parallel faces that are pointing in the same direction, both the normals will be a match and the point that we pass in will lie in the same triangle for both faces. This script currently just returns the first matching face found, which isn't always the correct one. To fix this, I started by adding an array of matches at the top of the function. And then, instead of returning immediately with the first face found, I get all the matching faces and push them into our array. I create the plane using the vertices of our triangle, like so, and this plane will allow me to get the distance at any point in world space to that plane infinitely. I then work out which plane has the smallest distance to our hit position. the face for the smallest distance will be the correct matching face. Now that we have our finished script, create a plain node in our scene and call it something like level UV position. Then attach our script to it. Now we just need to make sure that the correct mesh instance is assigned to the UV position node when the game is ran. Create a new script with the appropriate name. The script itself is really simple. We just need to get our level UV position node and call the setMesh method while passing our self in. Make sure the script extends mesh instance 3D. If you want, you could set up the level UV position as a singleton so it's always accessible via script. To do that, in the auto load tab of your project settings, add your script for the UV position. Give it a good name. Click add. And then instead of doing this, you can just access it through script, and then you don't need this node anymore. Now we just need to assign that script to the mesh instance of our level. If we run it, we shouldn't get any errors. Perfect, now we can move on to the drawing. First we're going to add a new sub-viewport to our scene. We then need to tweak a few settings. First, the size needs to be the same as the texture used on our level mesh. Then expand render target, make sure clear mode is never and update mode is always. Finally, we want a transparent background and we don't care about input. We're going to be making use of Godot's manual drawing functionality to handle drawing to our viewport. Start by adding a new node 2D as a child of draw viewport and call it brush. Then attach a script to it. Right at the top, let's add two export variables to our script. The first one will hold the texture of our brush, and the second one will hold the size that we're currently drawing at. Now let's override the draw function. This will get called automatically by the engine only once, but we can request a redraw for the next frame whenever we want. We may actually want to draw the brush multiple times per frame, for example if a collision intersects with multiple faces. To handle this, we're going to start by creating an array to hold our brush instructions. Each element in the array is going to hold a position and a colour, and we set up a method that we can call publicly to queue up our brushes. Finally, we call queueRedraw. This is a built-in method which will trigger the _draw method to be called again. It doesn't matter, this may get called multiple times because as per the docs, this will only happen once per frame, even if the method is called multiple times. Finally, to handle the drawing, we just need to loop over our brush queue and draw a texture rect at the right position. We just need to assign our brush texture. This is a quick brush texture that I set up in Photopea online. I think if you created like a really nice paint splat effect, that would look amazing with this. Maybe even have a list of different texture splats that it will pull from random, but just for brevity, I've just created this quick, simple, slight fade. Just quickly to follow best practice, I've attached a new script to the draw viewport. We're going to use this to encapsulate away the functionality of the brush, so we don't have to constantly access the child of draw viewport from externally elsewhere in the scene. We're only ever really interested in the cube brush method, so we're going to have a paint method in our draw viewport that we can call from anywhere, and then that will handle the rest. This helps as well if we want to change functionality later down the line. Now that we have a system in place to convert world space coordinates into UV coordinates, and we have a viewport with a brush that we can draw to whenever we want, we just need to trigger the drawing whenever a collision happens that we're interested in. I was originally going to use Godot 4's new particle collisions to handle this. However, I don't believe there's any callbacks with any relevant data that we can use, so we're going to have to write this ourselves. So this is the quote-unquote particle that we're going to be using. The main node is a character body 3D. The reason why we're using this is because if we use a move and slide functionality, we can get this kinematic collision 3D object back. This object will give us both the normal and position of the collision, which is exactly what we need for our conversion. The view node is just a sphere mesh instance that we've squashed down a bit, and then I've added an animation player with an automatic scaling animation, just so they look like they're getting bigger over time. Now it's time for us to work on our script. Our particle script is going to start off quite simple. First we export a variable to store the colour. This is the colour that we're going to draw onto the viewport later, and then the speed of the particle. We also grab the gravity from project settings. We expose a public method called startVelocity that's just going to update the velocity once we've set all the things that we want to in our emitter. And then in our physics process we're going to update the y with the gravity, rotate to look at our position plus velocity, so the angle changes as gravity pulls it down, and then we do the move and slide to update the position. Now let's create our emitter. Create a new scene and call it paint emitter. Then attach a script. Let's also add a timer. Let's set the wait time to 0.05 seconds. Set auto start to true. Make sure one shot's off. We're going to use this to trigger our emissions. So let's connect the signal now. For our emission script, let's start by getting a packed scene of our paint. We'll also create some variables that we export to hold some random variants of speed and rotation. And I've also set a boolean here that we can trigger the emissions with on or off. Let's also create the random number generator. Then, when the timer times out, if emit is true, let's instantiate the paint, add it to the scene, update the speed based on some random speed variants, set the position to the emissions position, and same for the rotation. Then we add some random variants to its x and y, and then we trigger that start velocity method to update everything based on what we've just changed. Before going any further, make sure that in your paint particle scene, the collision layer is on a different number to the mask. This means that these particles can't collide with each other and they can only collide with the ground. Now, if you add the paint scene to our paint scene, and then add it to our main scene, if we run it, you should see something like this. Now we just need to handle the collisions. In our paint script, let's get a reference to the draw viewport. Then, after move and slide, let's check to see if there was any collisions in this slide. If there was greater than 0, then let's iterate over all of them using getSlideCollisions_count. We can then get the collision for that index using getSlideCollision. We'll then pass in the position and the normal of that collision into our getUV coordinates, and then if we find a UV, then we're going to call draw viewport and we're going to paint with that UV. Although there's one more thing that we need to do. UVs are on a scale of 0 to 1, but our viewport works in pixels. Luckily we've abstracted the paint method away earlier, so all we need to do is multiply the position by the resolution of the texture. Now to actually start seeing results, we just need to create the shader. Go to the level mesh, make it unique, then change the surface to a shade material. Create a new shader. Here I'm going to use the visual shader graph. Create a UV node, and then create two texture 2D parameters. This first one is going to represent the level's original texture. The second one will be our viewport texture. Now create two texture 2D nodes and plug in our parameters and the UV. Then change the type on both to sampler port. Finally, we just need to mix these two colours together. I'm going to make use of the alpha channel on our paint texture as the weighting. We can then just put it into the albedo. In your new shader parameters, set the main colour to be the texture that your level uses. Now, if you're using a later version of Godot 4, you should just be able to also set the paint texture to be the viewport texture, but for some reason in the version that I'm using at the moment that doesn't work, but it does work if we assign it through script, so I'm going to do that now. Inside the script that we attached to our level mesh earlier, where we set the mesh for the UV calculation, we're also just going to set the shader parameter through script. Then if you run it, you can now paint. There's a lot of extra stuff you can do to this shader to really improve the effect. Here's just something I've done quickly where I've just grayscaled out the texture of the paint, added some noise, multiplied it together and shoved it into the roughness, which gives it a bit more of a paint sheen. This is just really quick and dirty, and there's some really cool effects you could do here. Here I've just downloaded a mesh and some animations from Mixamo and created a quick basic third-person shooter controller. And then I've added 2 emitters to the end of the gun so you can see the different colours. If I look at the light a certain way, you can see how the roughness has changed the texture of the paint. And yeah, you can run around your scene and paint whatever you want now. Finally, I'm going to show you how to handle the score calculation. Let's start by creating a new script. Call it score calculator. To handle the score calculation, the solution I came up with is to go through every single pixel in our paint texture and count how many are blue and how many are red. This is not something we're going to want to be running every frame or in the main thread at all for that matter, because for our example I'm using a 2048 by 2048 paint texture. That's a total of about 4 million pixels it's going to have to count through, and that will slow things down massively if we put that on the main thread. Let's start off by declaring a few variables. First, let's create variables for the red score and the blue score once we finish calculating them. Then let's store the thread. Then we're going to create a semaphore. Semaphores are great because they allow us to make the thread wait until we want it to do some work. Once we've passed some work over to it, we can then trigger it to run through it and then wait again until the next job comes in. This is perfect for our use case because we'll trigger this thread from the draw call in our brush, so that we'll only update whenever the paint texture gets updated, and the thread's not going to be running around in the background waiting for us. Let's also create a mutex. Mutexes allow us to kind of lock the thread, which allows us to safely join back onto the main thread and access any variables without causing undefined behavior. Then finally we'll create an exit boolean just so we can kill the thread once we're finished with it. And also we need to store the paint texture that we're going to be doing the calculation on. So now let's run through our main thread. First we're going to create an infinite loop so the thread will never end. Then we're going to begin by telling our semaphore to wait. This will halt the thread here until we call semaphore.post. Then it will allow the thread to carry on with the rest of its work. Then we're going to lock on our mutex so we can safely check if we should exit. And if it's true, then we'll kill the thread, which will finish everything else off. We'll lock again to get the image data. Then we're going to loop over all of the pixels within our paint image. And we're going to count how many are blue and how many are red. I've created it as 0.5 so that way if they're not 100% red, like for the fall off at the edge of our brush, or maybe when they mix together, I don't know if you noticed, but they can go purple in the middle because blue and red make purple, we can still count some of those pixels. Then finally we lock again to then update our scores. I'm dividing by 1,000 here just to make the scores a bit more readable, because like 4 million is a big number. And then finally on exit, we just clean up the thread. We lock, set exit to true, and then we post the semaphore one last time so it's not stuck waiting and it can come down and fall into this exit logic. Now we just need to create a method that we can call whenever we want to update our score. Here we're going to await on the rendering server to finish drawing the frame, and then once that happens we'll come back here and then we'll tell the semaphore to post and the thread will handle the rest. Go back to the brush script, create an onReady variable at the top to store the path to our score calculator node that we've attached that script from earlier to, and then at the end of the draw function just call recalculate score. Now all you need to do is create some labels and attach a script to them to set the label text to the scores from the score calculator, and you'll have something like this. So if we start painting down some red, let's see our scores going up. And then if we start painting over it, I'll paint some blue over here, blue goes up. If we start painting over the red with blue, blue score goes up, red score goes down. And then if we do the opposite, blue score goes down, red score goes up. And there's no lag or FPS drop due to this. Right, I think that's going to do it for this video. If you have any suggestions for topics or other game mechanics you want covered, please drop them in the comments below. If you like the video, be sure to subscribe and I'll see you in the next one. Cheers!